Right. Hello. All right, we are live. Hello.
Okay, very good.
Hello. Welcome. Thank you very much for coming to this talk. And we also like to start off by saying thank you very much to the DevOps organizers for this amazing conference and for having invited us here again. So you've come to this talk entitled, Why Haven't They Fixed This? Which is going to be presented by me and by Stuart, who is the man who hasn't fixed it.
Right. Okay, so where's your... Yeah, there you
go.
are. Okay. All right, so I'm Stuart Marks. I'm the project lead of the core libraries team at Oracle. I work on OpenJDK. I do a whole bunch of different stuff, but probably mostly what I'm responsible for is maintaining the Java collections framework. My alter ego is Dr. Deprecator, who will be making an appearance later in the conference. So he will see you then. I have a number of JEPs that I've worked on over the years, including a couple things on collections, most recently sequenced collections. And you can reach me on Mastodon.
Right. Thank you very much, Stuart. I'm Maurice Naftalin. I've done various things. I wrote a book about, I co-wrote a book about Java collections and generics a long time ago in prehistory.
It's the best book on Java generics.
Yeah, right. That's what I used to say for years. The best book on Java generics. Oh, it's the only one, but never mind. I wrote a book on streams, and for many DevOps conferences now, maybe 3 or something like that, I've come along and said, there's going to be a second edition. Well, do you know what? There actually is a second edition of Java generics and collections. Yeah, right.
Hey.
Yeah, just out.
Actually, that's the best book on Java generics.
Yeah, this is now the best book. It's definitely better than the first edition. So, I actually. Because this book is kind of quite new, I'm still trying to push it a little bit and maybe get more than 1 review on Amazon and maybe with something slightly better than 2 stars. And I've actually managed to organize for a box of these to come here, and we are going to. What would a talk be without prizes? So I'm going to give away up to 3 copies of this for the best questions that we get during the conference. And I have I've got an agent in the audience here monitoring the questions, and the 3 best questions, up to the 3 best questions, will get a prize. If there aren't 3 good ones, then, and then afterwards, I'll also sign them as well. To some of the remaining ones. Yeah, so come and see me if you would like a signed copy of this amazing best book on Java generics. Okay, so these are my coordinates. These are some of my coordinates. And I also organize something I really like to push in all talks, which is an unconference called JAlba, which is taking place next year in May. And the idea of an unconference, I would recommend you to look out for these. JAlba's not the only one, but it's certainly, I say, the coolest one. It's in Edinburgh, so
it's pretty cool.
It's very cool. Edinburgh's very cool. Even in the summer, it's pretty cool. And the idea of an unconference is that we mix together pretty deep technical discussions with also social activities as well, and they mix really well together. So it's experienced for 3 days. Up to maybe 20 or 30 people will get together, and we get really good technical discussions, and then we get outings and we go for nice meals. And of course, it's Edinburgh, so we drink whiskey, and the whole thing's just a great event. But all the people who come say that anyway. And it's a chance, I should say, it's an important chance if you want to mix with with very knowledgeable people and get deep knowledge from them. The unconferences are a really good way of doing it. They're not like this where people stand at the front and just tell you what's going on. They organize themselves, everybody gets a chance to speak. It's a really good event. I strongly recommend them. J Crete is the most famous one. J Chateau is happening in March, and then JAlba is happening in May. And there are others as well. So follow my socials to see how to find them. Right, I think that's enough about that.
Okay.
Okay, so today we're going to talk about all these things that are so irritating about Java. Concurrent modification exception is a pain. Everyone knows that because if you've ever had it, you know how painful it is. Mutating elements breaks value-based collections. Lots of people have had that experience. You put something into a collection, and then you can't find it again. type inference doesn't work. We have to keep on telling the type system what to do when it's really obvious. Set equality, we've got such weird things going on with set equality today. You will not believe it. And all this stuff about immutability, and there's no support for it in Java. What is the matter with these guys,
I know, what
Stuart?
What
is the matter with them? Okay, right, you're gonna tell them about concurrent modification exception.
So we are going to dive right into concurrent modification exception. So let's see, quick show of hands. How many people have had trouble with concurrent modification exceptions? Actually, pretty good, maybe over half or so.
Not that many.
All right, so yeah, so this is deeply intertwined with iterating of collections. And so here's a more precise way to phrase the question. So you have a collection and you have iterators. Why don't have collections have iterators that handle concurrent modification to the collection promptly and consistently? Okay, so let's go through a quick example to bring everybody up to speed. So let's have some code here. We create a list of strings and copy it into an array list, and we iterate that list. And for each element, we say, oh, if the string contains an E, then we remove it from the list. Okay, and so if you run this, it will throw a concurrent modification exception. And so why does this happen? Okay, so there's a conflict because you have two objects now in play. So there's an iterator in here. So the for each loop actually has an iterator inside of it. It's easy to forget, but it is hidden in there inside. So you have an iterator object that's hidden from you, and you have access to the list. And so they're both, you're operating on the iterator and you're also operating on the collection, and they come into conflict. And the iterator runs into some state and it says, oh, the collection has changed out from under me, this isn't working, throw the exception. Okay, and so the principle about this is fail-fast iteration. As soon as it detects a potential conflict, now it doesn't have to be an actual conflict, but as soon as it detects a potential conflict, it throws an exception because, hey, there might be a problem here. That's kind of the stance that it takes. So let's see. So what can we do to get around this? You might say, let's not use iterators. Let's index a list using indexes. After all, a list has a list. You can get things by elements, and so let's rewrite this. Instead of using the for each loop that uses an iterator, we'll use indexes. Okay, so we have the same list. We go from index I being 0 to size, and then if that element contains an E, we remove it. Okay, great. Did you write this code or something? Because it doesn't actually work.
Well, no, I thought the kind of obvious thing. I mean, clearly this isn't going to work because the index has been advanced when you moved it. So why don't you just step the index back?
Yeah, we could do that. All right. So now this is kind of interesting. It's like when you remove an element, it's like advancing the index, but the I++ in loop advances the index every time. So instead, well, if we remove an element, let's just decrement the index. Okay, and this works. It works in the sense that we get the result that we want.
Yeah, it's perfect.
But
it's not quite perfect, honestly. Like, it's going to work with lists, but all those other things, like hashed collections, trees, they don't have an index like that.
Right. So the problem is that this only works if your collection uses indexes. And so what this exposes is mixing the loop mechanics of going through every element with operations on the element that you want to process. And so when you mix those, sure, it works fine for a list, but it doesn't work for anything else. Okay, so what do we do? Well, so the recommended solution for dealing with removals from a list is to actually ask the iterator to remove it. So here we have to fall back to our old style for loop, where we take an iterator, we advance it as long as it has a next element, and then we say, okay, if the next element contains an E, then we ask the iterator to remove that element from its underlying list. We don't talk to the list anymore. Okay, so this works because the iterator talks to the list. But if you modify the list, it doesn't talk to the iterator.
It's a lousy solution, right? I mean, all those hands went up with concurrent modification exception. How many of those were actually real concurrent modification exceptions? I'm going to bet that hardly any of them were. You were just wanting to modify the list, and the iterator complained because it hadn't been told about it. So this isn't...
So why haven't they fixed this, Maurice?
Yeah, I don't know, Stuart. We should ask whoever's maintaining collections.
Okay, so now let's talk about the design of iterators. Okay, so we have an iterator, we have an object-oriented system, we have separate objects, we have requirements imposed on this new iterator object. And so one of the requirements is we want to have multiple iterations. They happen to be read-only, but if you have multiple read-only iterations in progress, they should be able to proceed independently. So that implies that you have to have the potential for multiple iterator objects. Now, there are other systems where if you have a collection, you can only have one iterator or one cursor. And that's actually really restrictive, and I don't think anybody wants to deal with a system like that. So when the Java Collections Framework was originally designed, they said, okay, we'll create an iterator, and each time you iterate, you create a fresh iterator that's independent of all the others. Okay, that's one thing. The second thing is, it is allowed for the application to abandon an iteration that is currently in progress. And so this actually makes a lot of sense, because you might want to iterate through a collection, and when you find the thing that you're interested in, you just return it or break out of the loop or whatever. So you don't want to have to be required to close an iterator every time you've created one. So between the two of those, well, okay. So and then also if you just abandon the iterator, then the garbage collector will take care of it for you. So that's great, right? But this has a bunch of implications on this concurrent modification problem. Okay. So if we want to avoid concurrent modification exceptions, then we would say, all right, we said earlier the iterator updates the collection, but the collection ought to update the iterator. Well, it's not one iterator, it could be many iterators. So the collection needs to track all of the active iterators, and it needs to keep track of them as long as they're active. And then there's a second problem, which is, okay, now that it knows what iterators are currently active, what does it do to the iterators so that the iteration continues to proceed correctly? So it needs to update the active iterators somehow. All right, so what's involved in tracking iterators? So, okay, so suppose I have an array list, and somebody takes an iterator, and then somebody takes another iterator, and we have several pieces of code that are iterating through the array list. And the array list now has the responsibility for keeping track of all these iterators that are active. And so where does it store them? Does it store them in another array list inside of itself?
Yeah, that sounds like a good idea to
right?
me.
But then
every collection has a little collection inside it.
Yeah.
Each one of those collections has a little collection inside of it.
Right. Well,
sounds good to me.
And that's true, because what the array list actually needs to do is iterate the list of collections. So
yeah.
Okay, so now all right, we can deal with this. We know how to write lower level code, but it's kind of a pain. All right, so but in this model we're constructing, where a collection tracks all of its iterators, every collection now needs to track its open iterators in an array or another collection or something like that. And so, okay, so we can just write more code and deal with that. The second thing is we have to know when we can purge that collection of iterators. Because if you allocated a new iterator and the list or collection or whatever added that to its active set, that would just build up indefinitely, and then you would eventually run out of memory. And so we need a way to say, if the iterator is no longer active, then it should be allowed to be garbage collected. So how do we do that? Well, one way to do it is by using what's called a weak reference, which is a facility in the JDK, which gets cleared when nobody else is referencing the actual object.
And when the JVM is under memory pressure.
That's right. Yeah, that's true. That's one of the times when it happens, but it's sort of whenever the GC decides to do the work of clearing references to unreachable objects, then that will happen. And so periodically what the collection will need to do is say, okay, I don't keep direct references to the iterators that are active. I keep weak references to those iterators. And every so often I have to run through and say, oh, this reference is cleared. That means nobody's using it anymore. So I can just actually take it out. So, all right. So there's actually a fair amount of stuff involved in doing that. And that's quite a bit of work. And also there's overhead.
Yeah, it's very expensive for the garbage collector because the garbage collector's got to keep a list of all these weak references so that it can go through and check when they aren't referenced anymore and recycle that memory. So like from both sides, the collection and the garbage collector, both of them have to do the work. So there's a lot of work, there's a lot of coding to be done here, and there's a lot of overhead in terms of computation.
Yeah, so don't underestimate the expense of bookkeeping that the GC needs to do for tracking things like weak references. Okay, so if we think that's too expensive and maybe too burdensome for a collection to keep track of all its iterators, maybe we should have a protocol for the application to tell us when it's finished with an iteration. Well, that actually cuts against a requirement we posed originally, which is you don't want to have we want to enable applications to be able to abandon an iteration in the middle and not worry about it. But here we're saying, okay, well, since we're keeping track of the iterators, we need the application to tell us when they're done. So now that means we have to tell applications to close their iterators. So I guess that means putting every loop in a try with resources or something like that.
Yeah, that would work.
Yeah,
but it's not. People aren't going to love it.
Yeah,
it's extra work for the programmer, and you're going to forget to do it.
Right. Yeah,
you will.
Yeah, and
really.
And the result will be memory leaks. Okay. So there are a bunch of problems with tracking iterators. Okay, but let's say we can write more code and figure that out. So what's the other half of the problem, which is we need to keep iterators up to date. Okay, so suppose you have an array list. The iterators, what's the iterator's internal state? Well, it's basically just an index into the array list. And so if you change the array list, then all you need to do is go update that index. So that's great, but what if the collection isn't an array list? What if it's a hash map? And occasionally a hash map will need to rehash all its entries if it needs to change size. And essentially what it does is it shuffles all the elements. And so if you're in the middle of iterating them and all the elements get shuffled around, what happens to the state of your iteration? I don't know, we'll figure something out. Or like a tree map. Like a tree map is a balanced tree. So if you study tree data structures, there's a trio of nodes that have to get rotated in a particular way. So if you're in the middle of an iteration that happens to be in one of those, and the nodes get rotated, how do you recover the iteration from that properly? I don't know.
Figure something out.
We'll figure something out. Okay, but actually, there's fundamentally a semantic weakness, which is, we're not going to spend any time on the details of how an iterator gets updated, but really let's think about what do we want the update to accomplish. So for instance, suppose I'm iterating some collection, like a list, and the iteration is in the middle somewhere and an element gets added. Should that new element be included or not be included in the current iteration? What do you think?
It depends.
Oh, come on. You can do better than that.
Okay, yes.
Okay, yes. So what should happen?
It should be included.
Okay, yeah. So now we have an array list and we're iterating it and we're somewhere in the middle, and a list you can say add it at the beginning. Okay, so the iteration point is after the beginning. So how are we gonna include the one that was the element that you added before in the iteration?
Okay, I was wrong. No, it shouldn't be included.
Okay, all right. So now we have an array list, and the iteration is somewhere in the middle, and we add an element at the end. How do you prevent that element from?
What I said. It depends.
Okay, maybe you're right. It depends. Okay, so it turns out that in general, if you want a definite answer, yes or no, it is or is not included in the iteration, it's actually really hard. And so, in fact, what some collections do, particularly the concurrent collections, is their answer really is it depends. And this is called weak consistency. And so if you're in the middle of iteration and you modify the collection, then suppose you add a new element. Does that does that appear or not appear in the iteration? It might or might not appear. It turns out that from the point of view of the iterator, every element that appears in the iterator has appeared in the collection at some time in the past. That's pretty weak.
That is pretty weak.
Pretty weak semantics. And so if you have an iterator with those semantics, it's actually kind of hard to program correctly. So you have to be very careful about making any assumptions or establishing any invariants after you finish the iteration, because you just don't know what happens if things are being modified during your iteration. So we kind of question whether weak consistency is what people really want. If you have a concurrent system, maybe you can cope with it. But if you don't have a concurrent system, then maybe you need to think harder about the semantics. OK, so let's talk about the strange case of array blocking queue. So remember a few minutes ago when I said, oh, OK, a collection could keep track of its iterators. And in order to avoid memory from building up, you could keep a weak reference to all the outstanding iterators and expire them when the weak references get cleared, and there are a few other cases where that happens as well. So in fact, array blocking queue does this. Every time you create an iterator, it creates a weak reference to it, and it tracks them in its own data structure. And every so often, it purges the cleared references out of its list. And whenever elements are taken or removed from the queue, it goes and asks the iterators to, well, it updates the iterators, basically. It updates all the active iterators to reflect the new state of the collection. So this avoids throwing concurrent modification exception, but in fact, it provides weak consistency. So that's that's the semantics it provides. But I think most importantly, the code to implement this takes about 40% of the implementation file of array blocking queue. And so if you look at it, it actually has to do a lot of work to make sure this is done correctly. And I think it's reasonable to ask, is this worth it?
No, it's not reasonable to ask. I mean, it's obvious that it's not worth it. Yeah. And it really is a strange case, because who cares about iteration over queues anyway? I mean, queues are not designed to be iterated over. It's not at all clear what the author of this class was thinking of.
Yeah, well, in fact, I think the original author of this class was skeptical. After he finished writing it, he was skeptical of whether it was actually worthwhile implementing this. Okay. So there you go.
It's an experiment.
Yeah. Okay, so that's what's going on mostly in the implementation stuff. But what I wanted to do is open this up to a survey of what different platforms, including Java, do with this problem, because this is not a Java-specific problem. And so I'm going to run through Java and a bunch of different other platforms, because they all have collections and they all have some form of dealing with concurrent modification. Okay, so first of all, quick review over the concurrent modification policies that are in Java. Okay, so the original, I guess we call them legacy collections now, vector and hashtable. You used enumerations to iterate them. And so if you did that, and if you had an enumeration, if you were enumerating a vector and you modified the vector, what would happen? Well, anything could happen, right? You might get repeated elements, you might get into an infinite loop, you might corrupt the data structure or something like that. So there was actually no concurrent modification policy. And I think this sort of problem was what led Josh Bloch to think of the idea of concurrent modification policies, in particular fail-fast, when he introduced the original Java collections framework in 1.2. And so that's what we have in JDK 1.2. The fail-fast policy was introduced, where concurrent modification exception is thrown as soon as the iterator detects that something might have gone wrong. So that was introduced in 1.2, but in general, for concurrent collections, you don't want that either, because throwing an exception is pretty drastic. You do want things to be able to be updated concurrently. And so that's where weak consistency was introduced. I talked about that before. So no exceptions are thrown in weak consistency. But like I said before, sometimes it's unpredictable as to what you're going to get. And then finally, also with the concurrent collections, copy on write array list implements a snapshot policy, which is really nice because you're always iterating snapshot, and you don't have to deal with concurrent modification. The problem is that every modification you make to a copy on write array list makes a complete copy. So it's very expensive, but it's useful in some cases.
If you've got a situation where you have a scenario where your data structure is going to need many more reads than writes, it's really good. It's really good. It's very fast. It allows concurrent reads without any problems, and it's completely safe. But writes are really expensive.
Yeah. Okay. So I'm going to move on to the next thing. All right. So I did some historical research here, and so I discovered that there was an old C++ library called ET++, which is an application framework for C++. And they put a lot of effort into what they call robust iterators. And the dynamics in a C++ system are different. They don't have garbage collection, but they have memory allocation issues. And in fact, they do all of this stuff. So if you have a collection and you have an iterator, or multiple iterators, the collection keeps track of each iterator that is open. And because of C++'s well-defined memory deallocation, if an iterator goes out of scope, it gets freed, and that unhooks it from the underlying collection. And if the collection is modified, the iterator is adjusted to appropriately as to what the modification was. And so it's easy to say this, but there's a paper here that I reference, and it's over 30 pages long. It's actually quite comprehensive. In fact, pretty impressive work. So for things like lists, it's pretty easy, but they ran into these problems, right? So if you have a hash table, what happens if you modify a hash table during iteration? How do you update the iterator? So they actually go through a whole bunch of cases and spent a lot of work. So again, I think that's impressive work, but I don't think it went anywhere. As far as I know, nobody uses this system or a system that has any similar characteristics anymore. In particular, the STL of modern C++ does not provide robust iterators. So I think this is great work, but it hasn't gone anywhere. Okay. Oh, wrong button. There we go. Okay, so let's move on to C++. So what does happen in C++? If you look at the specs carefully, you can see that C++ has the equivalent of collections, and you can have iterators, and you have multiple iterators that refer to a particular collection. But if you modify the collection in a particular way, it will invalidate the iterators. It's like, okay, is that a problem? Well, it might be. An invalid iterator by itself is fine. If you just throw it away, you're okay. But if you operate on an invalid iterator, then the result is undefined behavior. And undefined behavior in C++ can result in memory corruption, or your program can crash. So
it's like, aren't you glad that you aren't programming in C++? Honestly, I mean,
he said it, not me. But.
well, I felt it. The iterator is invalid. You haven't noticed, and your program's just going to do anything. It's spectacularly dangerous.
Right. So what you need to do is, if you're iterating collections in C++, you have to be extremely careful to make sure that you either throw away an iterator and don't leave it around if the collection is going to be modified, or you avoid modifying the collection when somebody might be iterating it. And so it's the programmer's responsibility to do that. And speaking of programmer's responsibility, so probably the first object-oriented system that had something called a collections framework is Smalltalk. And if you read some Smalltalk material, you'll see that there are some similar concepts to the Java collections framework. And in fact, I think the Smalltalk design informed a lot of the prehistory of the early collections framework design in Java. And so that's very interesting. But in a bunch of conversations about Smalltalk and concurrent modification to the collections, they ran into exactly the same problem. And so there are many discussions in a bunch of different places. In fact, this particular quote from Ralph Johnson, who was one of the authors of the Patterns book, he's one of the Gang of Four. In fact, it was referenced in the ET++ paper that I referenced that I mentioned on the previous slide. Ralph Johnson was asked about how do you deal with, if you're a Smalltalk programmer, how does Smalltalk deal with concurrent modification? The answer is you just have to be aware of the problem and avoid it. Okay, good. All right, so Barbara Liskov at MIT developed with her research team a research programming language called Clue that made a lot of contributions to programming languages and object design. They had a collections framework and a notion of iterators, and they had exactly the same problem. And basically, it's like, just avoid mutating a collection while you're iterating it. How easy is that? Okay. And then finally, I think Rust probably has one of the more interesting approaches, which is Rust has the notion of ownership and borrowing. And a borrow can be mutable or an immutable borrow. And so iteration performs, if I'm not mistaken, I'm not a Rust expert, but if I'm not mistaken, when I tried this out, iteration performs an immutable borrow, which prevents other code from mutating the collection, which is actually pretty nice. So they don't have the concurrent modification problem because you cannot modify a collection concurrently with being iterated. But what that means, though, is that if you do want to have a modification, if you want to iterate a collection and do some modifications to it, you have to do something like build up an edit list off to the side and then apply those after the iterator has finished. So borrow checker provides safety, but it also creates more work by pushing it around elsewhere. Okay, so in summary, I think we just need to cope with this problem. The industry as a whole seems to have given up on this. I've been unable to find any seriously active, large object-oriented programming system that deals with concurrent modification any more effectively than Java, any way that is more effective than what Java does. And so I think what we need to do is just to advise Java programmers programming techniques that avoid this problem. And so one is probably the best one, which is don't mutate collections in place. If you have a collection with a bunch of elements and you want to add and remove sub, what you do is you run through the elements and build up a new collection and do the edits in the process of copying the elements into the new collection. And so you can easily do that with like streams, for instance, like streams and filter and whatnot.
That's really the model for bulk data processing in streams.
Right.
And it just avoids all of these problems.
Yeah, just apply edits while copying instead of making edits in place. So another approach is the iterator API does support remove, and list iterator does support removal and addition at the location of the iterator. I think it's a fairly clumsy API to use, but I hear that people do make use of the list iterator construct. So that's one approach. Another one is instead of mutating while you copy, so to speak, is you could make a copy and iterate the copy and then mutate the original. So that's an alternative. Or there are higher order functions. Actually, I should mention Rust also does this. They have a bunch of higher order functions, and Java does as well. And a good example is remove if. So it fuses the iteration and the mutation at the same time. So with remove if, you say iterate the collection internally, but remove all the things that match this predicate. And then so that will work just fine. And then you can also iterate a collection, instead of mutating in place, write down what edits you want to make, and then when the iteration is done, you can apply them later. Sometimes that's a valid approach as well. And then as for what the JDK can do, it's there's no grand solution that says this will make all your problems go away. But sometimes throwing a concurrent modification exception is too drastic. And maybe, this hasn't been implemented yet, but if people find it useful, we might consider doing something like this, which is instead of throwing an exception when something like that occurs, log a message or post a JFR event. And at least that tells somebody that something is potentially gone wrong, but instead of throwing an exception, just terminate the loop or something like that. And maybe that in certain situations that might be more amenable to interrupting processing by having a concurrent modification exception be thrown. So if anybody's interested in something like that, let me know.
Wow, wow. So they're actually, you're talking about a fix. You're actually thinking...
Occasionally I do write code, Maurice.
Right. Okay, so it's not entirely pessimistic, this one.
Yeah.
Okay, that's the story then for iterators and concurrent modification exception. That's why you've got it. And this is why you want to kind of pile in those, I don't know, what, on your socials or bug reports. Yeah, tell them to get something done. There's actually is a way out of it. Warn and continue. Interesting. Okay, so that's the first of our irritations. Here's our second irritation. Mutating collection elements. But why do collections handle element mutation so badly? What do I mean by that? Well, you've probably seen this. I'll go over it fairly quickly. Here's a slide with a lot of code on, but this code is just a POJO. That's all it is. It's a person class, and the person class has a string name and an integer, an int age, and the only thing that makes it anything other than a completely standard POJO is the fact that it's comparable. It implements comparable, and two person objects are compared by age. So I don't want you to read this code in detail, but just take my word for it that there's really nothing unusual going on there at all. Though I suppose it's probably worth pointing out that the oh, that didn't work very well. Oh, because it went backwards. Right, let's try this again. It's possibly worth... that does work. It's possibly worth pointing...
Okay.
But I'm still in the wrong place. I'm going forwards. Sorry about this. Let's have another shot. Right, here we go. Right, okay. This is what I want to do. Trying to do clever things is a bad idea. So the equality method begins with an identity check. That's all I wanted to point out there. A lot of trouble to do that. Okay, so here's some code that uses the person object. So what we've got here is that we create a new person, and this is Lucy. She's 25. We put her into a hash set. We check. Here we can check that she really is in the hash set. Yeah, that's true. Then we alter her age, and then we check that she's still in the hash set. So we can if we stream the contents of the hash set, yeah, she's still there. E equals Lucy. Yeah, that's right. Or we can do it with an identity check. Yeah, everything's right. But if we ask whether the hash set contains Lucy, it's false. Right? What's going on?
That's pretty amazing. Lucy is simultaneously in the hash set and not in the hash set.
She's kind of Schrödinger's Lucy.
Yes.
Right. So what's going on here? Actually, that's absolutely true. She is still in the hash set, but she's not findable in the hash set. Why not? Well, here's a picture of the hash set when Lucy is still only 25 before the clock ticked on her age. So the hash set is a set of it's an array of buckets. It's 16 long by in the default before it's resized, and as it happens in this case, the last one's pointing to a node that contains a pointer to the Lucy object. It's a linked list structure, so other things could hash with the same code. So how do you find Lucy? Well, the answer is you calculate Lucy's hash code. In the POJO definition, we said the hash code is going to be 31 times the hash code for the strip for her name plus her age. That's a pretty standard way of defining a hash code. Now, how do you calculate the displacement of the bucket that contains the reference to Lucy? Well, the answer is this is what the hash code does. This is what the hash table does. It takes the hash code and it does an exclusive OR with the hash code shifted 16 bits to the right. and then it masks that with 15 because that's the length of the array, and it gets a number. In this case, the number it gets is actually 15. So the details don't count very much, but you can see that what's happened is that, amongst other things, Lucy's age has been factored into this. Right? So what happens when we changed her age? Well, what happens when we change her age is that now it's using a different calculation to find her. And by the way, the actual element has had its value changed. But what's the calculation going to produce now? The calculation, because the bottom bit has altered, because her age has gone up by 1, the exclusive OR actually ends up with a smaller number. It's only 14. So it's going to go looking for her in the wrong place, and it'll never find her. That's why contains returns false. It's pretty straightforward when you.
But if you enumerate all the elements, she's still in there.
Oh yeah,
because that goes straight through the buckets and follows all the linked lists.
Absolutely, it's the contains method that doesn't work. But the contains method is really important because the reason why we have these things in the first place is so that contains will be fast. But now it's fast, but doesn't work. Well, which do you want? Do you want it?
Yeah.
Do you want
Fast or correct?
Fast or correct? You have a choice. Okay, so that's what happens with hash sets. So something kind of pretty similar happens with tree sets, which are organized by they're binary trees. So in the case of the tree set, we've created a new tree set here, and we've put Lucy into it, and then we put Charlie into it as well. So Charlie is 27. Lucy at this point is 26. So we add Charlie to it, and then we check. We can check again. Is Charlie in the tree set? Absolutely, he is in the tree set. Well, we just put him there. We'd expect him to be there. Now we increment Lucy's age. Actually, we got it wrong. So we're going to actually add 2 to her age. So now she's 28. And what about Charlie then? What's happened to him? The answer is we can't find him anymore. Right?
So sending Lucy on a trip through a black hole or something caused Charlie to disappear. That's really. People thought quantum physics was strange. This is really strange.
So what's going on here? Well, it's pretty logical. So what happens is when you're looking for Charlie, what you do is the first thing you do is you look at the root node, and you see, well, what's the value here? Well, the value here that we're comparing on is 26, and Charlie is 27. So we'll go down to the right of that because the right subtree contains elements which are all greater than the root node. So Charlie's 27 there, and the blue arrows show that when we go looking for him, we'll find him. But now when we increment Lucy's age to 28. We're there, yes. Mm-hmm. So we increment Lucy's age to 28, and now when we go looking, well, we come in and we look at the root node. Oh, actually, the first node, the root node is 28, and we're looking for something with an age of 27, so it must be in the left-hand subtree. No wonder we don't find it. This is a mess.
It's terrible, isn't
Stuart,
it?
why haven't
we fixed that?
Right. You've done it again. So, collections that rely on element values. What are we going to do about this? Well, what do you think?
All right. Well, so maybe every collection should be aware of what elements it contains and be notified when one of those elements changes.
Absolutely. Hashed and tree-structured collections are organized by element values. Sorry about that. Collections like lists are organized by insertion, so you don't have this problem with them. Their order won't change when the values change because it depends when you put things into them. But these collections that we're talking about now, these assume that elements don't change value because they're unaware that when the value changes.
Yeah, so maybe that's the problem.
Yeah,
so maybe
problem
is they're unaware.
Yeah, so what we should be doing then is making the collection aware. It's a bit like actually the last one, isn't it? Mm-hmm. It's a one-way. It's a one-way link.
Yeah, there's a missing link.
Yeah.
Right? So if you modify an element, the collection doesn't know about it. So
what we should be doing is making sure that the element, when it has its values changed, should tell the collection, and then the collection can adjust itself. What would be a good way of having the collection adjust itself? I mean, in these cases here.
I don't.
All right.
I don't know.
I think what would be kind of a kind of obvious way of having an obvious foolproof way for all collections would be remove the element, and then put it back in again. So you'll remove it from the place where it was, and you put it back in with the new value, and the collection will still be properly organized, right?
Yeah, I get that might work.
Okay, right. Let's try this. So we need a connection from element to container. There are two options for how you can do this. I'll go through them both pretty quickly because we'll not be wildly excited about either of them, to be honest. The application could create a collection-aware object, one that knows that it's being held in a collection and so can inform the collection. Right? So that's one possibility. But that's going to turn out to be pretty intrusive because now you can't just have a straightforward person object. You're going to always have to add extra equipment to the person to make it aware. There'll be no such thing as a POJO any longer. POJOs will all have to be equipped with all this extra apparatus to tell their containing collections about them. So we'll have a look at an alternative where we'll actually have the collection create a proxy for the object, and now the programmer can use a person POJO class without any difficulty, and the collection will look after a proxy which will do the communication. So we'll look at both of those, and to be honest, you won't like either of them very much. But let's have a look anyway. So here's our first attempt at it. This is the containment-aware element. This is the simplest possible solution you could have. Einstein said everything should be as simple as possible, but no simpler. So this one you might decide is possibly a bit too simple. But no simpler. Maybe this one is. So all that we've got here is a containable person, and it can be put into any kind of collection. And the key thing is that when you change the value of a property, it notifies the container to remove itself from there and then to add itself in again, right?
So let me get this straight. So if you have a collection, and suppose it's a concurrent collection, so another thread will see Lucy disappear from the collection and then reappear. And so the size will go down and so forth. So the collection if you're modifying things, the collection size will constantly change. Or worse, if I want to add Lucy, I might add a duplicate Lucy.
Yeah, you're quite likely to do that.
So
there's this period when the object's absent from the collection. I mean, that's aside from other problems that we'll come on to, but that might be the first one that would strike you. So here's a better way of doing it, and there's actually something kind of quite useful in this better solution. This is a better containment-aware element, and the idea of this one is that it'll have a method on the collection now. We'll change collections so that they can be notified. So they've actually got an update element method, which will contain a runnable, accept a runnable, and that will do the updating. So it'll do the updating both of the element and also of the collection as well. So we're handing all the responsibility over to the collection. So this is actually kind of good. When set name is called now, then the container, the method update element is called on the container, and it supplies this lambda. So it says, remove me from there. What the container will do is it will remove the person from the collection, and then it will apply this runnable. It'll run the runnable, which will change the value of the property in the element, and then it'll add the element back onto the collection.
Okay, but it doesn't actually remove it. It just sort of marks it in a special way, so that it's still logically part of the collection.
Yeah.
But then after it gets updated, it knows where the old location was, so that it can hook it into the new location.
Yeah.
Okay.
Right.
Maybe that'll work.
So this is going to work. That's kind of a nice idea. The reason I kind of put that box there is because you're passing a behavior over to the collection. And that's definitely a better idea than trying to do it yourself. So that's one option, but the problem with this is then now the containable person has to have all this extra apparatus It's not a POJO any longer. It's now got to have every method that might change the properties that are going to be used for in one of these value organized collections. It's going to have to change the setters for that. Every time any of those properties get changed, it's going to have to call update element on its container, and it's going to have to keep a record of its container. So that's quite intrusive. So a different possibility would be to have the collection create a proxy and have the proxy handle all of that. So the proxy will have to intercept all the calls to the original POJO, and the code is going to look something like this. So because we definitely want to make sure that nobody will ever modify the POJO, they'll never call set name on the POJO without going through the proxy, what we'll have to do is have the collection create the POJO and never let the reference to the POJO escape. So the collection will get a supplier, like it'll get a reference to a method reference to the constructor for the POJO. It'll create it, and then it will then create a wrapper object, which is the proxy, and that's what the application will then use. So the picture will look a little bit like this. So now we've got this we've got a Lucy wrapper here, which is a proxy object. It's going to have the same API as the POJO had, and that can now be stored in the collection. Whenever set name gets called on the proxy object, it can then notify the collection again. So that's how this idea is going to work.
Okay, so you can't just create a POJO and stick it in a collection anymore. You have to have the collection create the object for you and return a proxy that has the same API so that it can intercept all the calls.
And now the proxy has a connection back to the POJO. So we've established this two-way connection that we needed. So now it's the proxy that is containment aware. It informs the container of the updates. So all application updates must go via the project, via the proxy. Sorry, has to have the same API. That's simple enough if you've got an interface. Well, we've been talking about POJOs, but I mean, if Lucy was actually an interface, then we've got the Java lang reflect proxy. A feature of Java that was introduced in Java 1.4, which creates proxies like this, dynamic proxies like this, automatically for you. So it's a very nice feature, but it doesn't work on classes. You've got to use something else. You'll have to spin the bytecode with some library like ByteBuddy, which is there for that. So the advantage of this is that you now don't have to create a containment-aware class. The disadvantage is you've got a lot of tooling to cope with. And well, we actually haven't talked about the previous problems, but we're going to talk about the previous problems now, because this slide got reordered.
Right, that's all right. Well, why don't you bring up the next slide? And
Okay, right. Right, because do you know what? We haven't even begun to cover the problems here.
Yeah.
There are many more problems.
So I think we've reached the stage in this design where we're breaking up new stuff. It's like, oh, well, yeah, that's a problem, so we'll come up with a solution to that. Well, every solution we come up with creates more problems. So that's kind of what's going on here.
Elements could. So here's one.
Yeah.
Elements could be a member of more than one collection. So actually, we can cope with this. So you can imagine the element might have a register of the collections that it contains. That contain it, and then you'd have a registration method and deregistration methods on the element to tell it what collections it's part of, because other collections wanting to be there would have to be able to be informed when the values had changed.
Right. So but then we had this nice protocol where we had this update element on each collection. You couldn't just for each over the collections that contained it and update them one at a time, because after the first one, it actually mutates the object, and then subsequent ones will only see the new version of the object, then they won't be able to find its old location. So what we really need is something like a two-phase commit. right? And this is why, say, Oracle's a database company, so we got to do all this stuff, right? So you have to say, okay, I want to open a transaction, and I want to reserve, something, go through them all and say, I'm going to mutate this thing, and then push it forward in a transaction and so forth, right? And since it's like a transaction, what if your update method throws an exception? Well, you're going to need to roll it back as well. So now we're creating a database inside the JVM.
Okay, well, Oracle's a database company.
Yeah, we can do that.
Right. And do you know what? We still haven't found all the problems. Here's another problem.
Yeah.
Which properties are being used to organize the collection? Right. I mean, in the case of Lucy, it was straightforward because you could see what the hash code created, and you could see what the natural order was. Right. So the hash code used the name and the age, and the natural order of person, the way it was defined right in the first slide, was ordered on age. Fine. Okay. So we would know to proxy the set name and the set age methods. But what about if you had a tree set that was ordered on an external comparator? Well, you don't know what the proxy doesn't know that that is going to happen, or the containable object doesn't know that that's going to happen. So which properties does it use to notify the container? It's not completely obvious.
You just need to expand more APIs to figure this out.
Yeah, well, actually, you could do that, couldn't you?
Yeah,
because when you put this object into a tree set with an external comparator, you could supply the comparator or a list of the properties that are going to be used.
Yeah,
I like this API. It's working out really well. Okay, so but maybe you've got an idea about. I mean, this is just us thinking aloud, really, and I'm sure we haven't got to the bottom of the complexities. So why haven't they fixed this? The reason they haven't fixed this is it's a really hard problem. I mean, it really just doesn't look like it's going to be worth it. The solutions that we thought of, maybe they're not the best possible solutions there could be, but these are like kind of reasonably obvious ones, and they're intrusive and they're elaborate and they're not going to work most of the time. They're really fragile. So, what should you do about this? Well, the answer is just don't. The programmer needs to be aware of this problem and avoid it.
That's right.
In the immortal words of Ralph Johnson.
Yeah, I think he was definitely right in this case as well.
Yeah. So don't mutate the values that you're putting, or if you absolutely have to mutate them, then you're just going to have to remove your object from the value ordered collection, and just live with the fact that it's going to be absent from there at the time, or I don't know, lock the collection or something. But the programmer needs to be aware of the problem and work around it. That's about the size of it. Okay, what do you think? Should we let these people go?
I think so. So we've gone through 2 segments. We have 3 segments remaining, and so we do want to take a break. Actually, sorry, we didn't mention this earlier. We did have the 5 segments. We do want to take a break between, and I think probably now is the time to do it.
I think now is the time to do it.
Because why don't you advance the slide there?
Yeah, okay.
Because the next one is about type inference, and I think if you have the post-lunch doldrums, you are going to want a cup of coffee before we dive into this. So should we? How long?
Half past.
25 minutes.
Oh, sorry. Yeah, 25.
Sorry.
So no, I've got it the wrong way.
No. That's
that's the time we've got left. So it's 25 past now. So we say come back at 10 to.
Yeah, come at 14:50.
Right, 14:50.
Okay. Yeah, 2:50 p.m. Okay, great. Thank you. I'll see you in 25 minutes.
I don't know. I'm going to end up with a lot of these stupid books.
Okay. All right, welcome back, everybody. All right, so...
thank you for coming back.
Yes, thanks for coming back. Exactly. All right, so type inference. Why does it fail in really obvious cases? All right, so I'm going to take a whirlwind introduction through type inference here. So Java, as you know, is statically typed, and every expression has a type. There are a lot of explicit type declarations in Java, but there are a bunch of places in the language where types are implicit, and in those cases they are inferred. And so, for instance, a static method call like list.of actually has type parameters, and you almost never have to type never have to make the parameter explicit because it's often inferred. Same with var. Var is another form of type inference for local variables, and Lambda expressions also use type inference quite heavily. Okay. Now, type inference does not always work. And so sometimes you can be in the middle of writing code and type inference will fail. And you will get some weird compilation error. And you might say, everything worked before. Why doesn't this work? And so we have two examples here of where type inference can fail. One is with overload resolution, and another is with chained method calls.
We chose these examples because they were the ones we thought of.
Yeah, they're the ones we thought of, but we thought of them because they actually come up fairly frequently. Okay, so let's talk about overload resolution. All right, so this is a little bit involved, but I'll try to run through this pretty quickly. We have two method declarations of bar. They have different argument types or parameter types, and they have different return types. And we have a call here, list of string r equals bar, and then there's a lambda. Okay, so you can clearly see the need for type inference here because no types are provided in the lambda. Now, if you dig into this, it turns out that overload 1 will work, and overload 2 cannot possibly work because if you try to look through this and make things match up, it just doesn't work, or does it? So what happens when you compile this? What do you think?
Well, it's obvious what happens, right? Because you've got something that works and something that doesn't work, something that doesn't match. So 2 doesn't match, 1 does match. So the answer is that it'll compile against overload 1, right? I mean, that's what you'd expect. That's what you'd expect in any other context.
That's what you might expect, and in fact, quite reasonably so.
Yeah.
But instead, you get this compilation error that says reference to bar is ambiguous, and so this is actually a pretty common question, which is all right. So it says it's ambiguous. There's this bar method and there's this bar method, and they're overloaded. But if you look at it, one can't work, or one can't work. So how is it ambiguous? It's not ambiguous. One doesn't work. So the other one should work. So why haven't they fixed it?
Yeah. Well,
why haven't we fixed it?
Well,
I'm not on the compiler team, so why haven't they fixed it?
Yeah, right. We can blame somebody else. We can blame the compiler team for this.
Right. Okay. So I'm going to try to do a quick overview of what type inference actually does when it sees this. Now first, I'm going to take the overload declarations in isolation. So here, just forget about the second declaration of bar, and we have the first declaration of bar, and we compile a call to bar against that. Okay, so the return type declared by bar is list of t. Okay, so we don't know what t is, but we're going to have to figure that out. Now, in the let's see, is this?
You're on the wrong button. Oh, that's the...
Is this? There it is. Okay, all right. Well, I don't know. Maybe I shouldn't...
No, you're okay.
Yeah. Okay, it takes a little while.
Yeah.
All right. Yeah, this is a little... All right. So in the call to bar, it's an assignment statement. It's on the right-hand side of it's actually a variable declaration. And the left-hand side is list of strings. So that provides the target type. And so since the return of bar is list of t and the target type is list of string, the compiler knows that t is string. Good. Okay. And then let's look at the parameter for bar. It's declared as a toInt function of t. So that takes a t and returns an int. And so you have to kind of know you have to have the definition of JavaTL function, the functional interfaces in your head. But that's what the toInt function functional interface does. It takes a t and returns an int. Okay, so now the lambda, so we know that t is a string, so the lambda gets typed as toInt function of string. So that means it takes a string and returns an int. And sure enough, if s is a string and you call hash code on it, that returns an int. That works. Great. Okay. So now what happens if you... so you get a flavor for what type inference is actually doing. Okay, so now let's say we have bar declaration number 2 in isolation with this call. All right, so here the return type of bar is u. The assignment context, again, provides a target type, which is list of string. So u is inferred to be list of string. Now, it's also kind of interesting that we have another type variable t here, which is unconstrained. Okay, So the argument, or sorry, the parameter to bar is function of t comma u, which takes a t and returns a u. And so the lambda takes a t, which can be anything, so I put a question mark there, or wildcard, and it returns a list of strings. So the lambda has to be a function of question mark to list of string. And that doesn't work because there's no way for hash code to return a list of string. So if you try to compile this, this doesn't work. So that's digging into the details of why overload 1 works and overload 2 does not work. Okay. Now, then the question is, if we know that's the case, why doesn't, if both overload declarations are present, why doesn't the compiler choose one of the overloads? And the answer is that you have a multidimensional space that the compiler is trying to find a solution within. So you have variables, you have a bunch of choices. The compiler needs to make a bunch of choices to see if your program can actually compile. And so the reason I say it's a multidimensional space is it's not just inference of types, but there are other things going on as well. Like, for instance, overload resolution. So it has to find an overload resolution, and it has to infer types that work. Okay. And there are also other things thrown into the mix, like auto boxing. And so actually the space is very complicated. But anyway, so if you have a multidimensional space, suppose you're able to look at an oracle in the computer science sense. So you say, is there a solution or not? If there's no solution, well, clearly the compiler should issue an error since there's no solution. But also, if there are multiple solutions, well, that should also be an error because it means that what you wrote is ambiguous. It could be this or it could be that. And you don't want the compiler to choose one. If there are multiple ones, then it should say, you need to disambiguate this somehow. Now, there's some complexity within this multidimensional space. There are types that need to be inferred and overloads that need to be resolved. And so in order to do overload resolution, the compiler needs the types of the arguments. But in order to get the types of the arguments, you need to in order to do type inference, you need a target type. And in order to get a target type, the compiler needs to have the overload resolution done in order to figure out what the target type is. So now you have a circularity. You have this weird thing where I can't do this before that, and I can't do that before this. So what do we do? Okay, what the compiler actually does, and this is not just the compiler, this is actually written into the language spec. It says, okay, here is how the compiler resolves the type of expressions. There are a bunch of rules, but it basically says overload resolution is performed before type inference on arguments. And that breaks the cycle. Unfortunately, it means that sometimes the compiler cannot find solutions that seem to be there, but basically they are disallowed by this rule. Okay, so there's a design principle going on here, which is that the designers of the language in the compiler said, we are going to use a linear process for searching this multidimensional space. We're going to do overload resolution before type inference of arguments. So that's what I mean by linear. We're going to do one before the other. Now, what benefits does this provide? Well, it provides predictability for the programmer. It means that the compiler is actually simpler and higher performance. And we'll see what happens if we choose an alternative design. But also, it actually makes the language simpler to understand, because since one of the outcomes of this is that the compiler is using local information in your source code to try to resolve these issues. And so if there's a compilation error, it usually means that the error is on the line that the compiler points out. And that's not necessarily true, as we'll see in the alternatives if we see. Okay, so we said the language in the compiler chooses a linear process for resolution and type inference. We don't have to do that. I said there's a multidimensional space, and there are ways to search a multidimensional space. You can just create a recursive algorithm that chooses a value and then searches all the solution space in that value and sees if there are any solutions there, and then chooses another value for the first thing, and then searches the space under that. So you could write a recursive algorithm that searches this whole space and finds all the potential or all the candidate solutions. And again, if you so when you're searching one of these spaces, you get to the it's like traversing a tree. So when you get to the leaf of a tree, all right, so either that's a dead end or it's a successful solution. You have to backtrack and change one of your upstream choices and explore a different subtree. Okay, so I think it's pretty clear that if we were to have such an algorithm, it would need to search the entire solution space. Because suppose there were multiple solutions, you don't want to stop as soon as you found one, because there might be some other solution and your expression might actually be ambiguous. But if you found only one and the compiler just chose that, that would be pretty unpredictable as to which of the ambiguous solutions that it chose. So we really want to search the entire space. And again, if there are 0 solutions, that's an error. If there's more than one solution, it's an error. But if it finds one solution, maybe it should use that one. Okay. So why don't we do this? The answer is that, I mean, there's a bunch of reasons for the answer, but part of this is that the search space includes constraints that are collected from all over your program. And if you have a backtracking search for the solution space and you change one part of your program, then that might cause the meaning of another part of your program to change. And we kind of don't do that. And I'm going to show an example of that. And so Einstein would have referred to this as spooky action at a distance. You make a change over here, and it has the effect of changing your program over there.
It's quantum entanglement. He really hated it.
Yes, and so do I, actually. Okay, so, but then there's also some other things, which is if you have a large solution space that you need to search recursively, that actually impacts the performance of the compiler. And there are systems for which where the compiler actually does this, and compilation speed is an error in such systems. Sorry, it's not an error. It is an issue in such systems. And it also might result in code that if you make a change to the code, your compilation might slow down. And so now you don't have to worry, you don't only have to worry about the performance of your code, you also have to worry about the code you write affecting compilation speed. So that's kind of a novel thing to have to worry about. Okay, so let me go through an example of what would happen if we had a backtracking search for type inference in Java. Okay, so we'll go back to our previous example where we have 2 overload declarations of bar, but then I've changed the call of bar so that the return value of the call to bar is passed to some other method. And other method takes a list of string as a parameter. And so the types are all the same, and so all the analysis I talked about previously is the same, and overload. So here we're suspending disbelief and saying, suppose the Java compiler had a backtracking search. So it would determine, just the same as we did earlier, that overload 1 works and overload does not work, but it will find the solution under overload 1. So bar will resolve to the first overload. Okay, now suppose through code maintenance, somebody decides, oh, I'm going to change the signature of other method. And so I'm going to change that from list of string to int. Now that's kind of a strange thing to do, but when you're working on code, sometimes what you do is you say, actually, that's the wrong thing. I'm going to make a change. And then the compiler is going to spit out a bunch of errors, which are going to tell me all the call sites that need to be updated. And so, okay, we might do that. So actually, it should take an int instead of a list of string. So unfortunately, this has the effect of silently changing the overload resolution of the call to bar when it's passed to other method. Because the target type that other method provides is now int. So that directs the search. It disallows this solution over here, and it enables this solution over here. And so now we've actually changed the meaning of this call to bar. And the problem is other method might be in some other class somewhere. So now we have a situation where, okay, we're going to change other method. We need to update all the call sites. But we never see this one because the compiler said, oh, I know, I can find a solution to that. And it's going to change which method gets called. So as a rule, we do not like making silent changes to programs' behaviors. So I think this is one of the reasons we don't apply some kind of sophisticated backtracking search to this problem of type inference and overload resolution. Okay, so now let's step back from this and return to the real world, where we have this linear process where we have overload resolution performed before type inference, and sometimes it fails because we've decided we're not going to search the entire solution space. What can you do? Okay, what you need to do is provide explicit type information somehow, and that guides the compiler to producing the code that you want. And so there are a couple different ways to do this that we see repeatedly. One is, okay, so the call to bar with the lambda, that's where type inference fails because it can't infer the type for the lambda. So instead, what we can do is we can say, oh, let's use a method reference, string hash code. That actually does include more type information because we've named string, and so essentially the parameter type for the lambda is string. And so that gives enough information to the compiler to succeed. Another way is to
well, mostly. I mean, provided the method reference that you're giving there is not to a method that's overloaded.
That's true. Yeah.
So it doesn't always work. So the fallback in that case is to go explicit. So the middle blue line there.
Right. Okay, so it's nice to use a method reference, but you can't always. Or if you need to pass a parameter to a method or something like that, you can't use a method reference, and that's unfortunate. So the next best thing is probably to supply an explicit argument declaration for the lambda. So say instead of s arrow s.hashcode, say string s arrow hashcode, and that will work. And then a third way is to put an explicit type parameter using this bracket syntax following the dot, which is a bit obscure. But sometimes it's the best thing to do. But in this case, the syntax of the language requires us to qualify it with this class, and so that makes it kind of clunky. But that is a possibility for how to provide additional type information to the compiler in such cases. Okay, so moving on to chained method calls. All right, so here's our second example of type inference failures. We have a person record, and the person has a last name, which is a string. Then we have a list of person, and now we want to sort it. And so if we say list.sort comparing person arrow person.last name, and this works okay. So suppose we want to do a reversed sort. We just add reversed onto that expression, and this should work, shouldn't it?
Well, it's kind of obvious, right? You've got a comparator of t, and reversed. So what you're looking for is a comparator of t. Reversed is something that takes a comparator of t and returns a comparator of t. So it's like it's obvious.
It's obvious.
It's obvious. Yeah. I mean, like if I can do it.
Yeah. Except that it doesn't work. All right. So error cannot find symbol method last name on type object. And it's like object. Where did object come from? There's no object in here. It's like, well.
Well, no, there is no object. Oh, why haven't they fixed this? Sorry. Right. Why haven't I read the slide?
Right.
Why haven't they fixed this?
Yes. Okay. So here we're gonna play compiler again, and I'll run through the analysis really quick. All right. So here we have list. Okay. So we have this expression here, or the sort statement. Okay. List is a list of person. List.sort takes a comparator of person. And now we have to do type inference on the lambda. So comparator.comparing returns a comparator of t. So that's how we know that t is a person. And then the argument to compare.comparing is it's actually more complicated than this because it has like wildcards and stuff. But essentially, it's a function that takes t and returns a comparable. And so we know that t is a person. And so the lambda calls last name, which returns a string, and a string is comparable. Great. So this works. So that's why the first line works. Okay, so let's try to do this again. So Same thing. List of person, list.sort takes a comparator. Now comparator.reversed. Okay, so that takes a comparator, that returns a comparator of t, but it's also an instance method on comparator of t. And so therefore t is a person, and then basically the rest of the analysis is the same. And so you might think this should just work.
You might think that.
And it doesn't. The reason it doesn't is that actually this expression is actually a different kind of expression from what we saw before. So this step in the middle where we said comparator.reversed it's an instance method call on comparator of t and returns a comparator, all this stuff. We were hoping that would work. But in fact, the compiler doesn't do this step in the analysis. And in fact, here's the rule. Okay, so when we imagine that stuff in blue. So that stuff in blue is it's just a method call. But then we chained reversed onto the end. And so the sub-expression in blue is now the receiver of a method call. And by rule, target typing does not apply to the determination of the receiver, the determination of a type of the receiver of a method call. Okay. So that's why it fails when you add reversed, because it actually takes that comparator.comparing person, that blue hunk, it actually puts it into a different place in the syntax where target typing does not apply. And so since target, actually I have this on the next slide. Okay, so why doesn't target typing apply there? I mean, it seems like it should. Well, the answer is actually exactly the same as I said in the previous one, right? We have this multi-dimensional space that the compiler might need to search, and we don't want to do a recursive backtracking search in order to do that because of all the reasons that we just said. And so really, the compiler has made some simplifying assumptions that says target typing does not apply here, and so the type of the receiver of a method call must be determined before method resolution is performed. And so that has the same effects. It simplifies the compiler, makes it more predictable, but it also means that certain cases will fail to compile, even though it looks like they should. And so anyway, so the receiver in this case has a type variable t, and since there is no target typing applied here, t is inferred to be object, and then we try to call last name on it, and it says there's no last name method on object. And so we're saying, where did object come from? Well, that's where it came from. Okay, so that's why it doesn't work with chaining. Again, we have essentially the same techniques. You can use a method reference here, and it works just fine. If you can use a method reference, you can't always, or use an explicit lambda argument type, or use explicit type parameters in the call. And once again, we have the explicit type parameters R being the third string here, because you have to understand the type parameters that comparator.comparing takes and put them in the right position. It's pretty obscure, but in fact, that supplies the exact type for comparator.comparing, and that will work. Okay, so quick summary. All right, so type inference in Java is kind of an 85% solution. And there are lots of reasons that people would want a 100% solution. It would be nicer if that were done, but it doesn't. And it doesn't for good reasons. It works most of the time, and when it doesn't work, it gives up quickly. So it doesn't spend a lot of time searching for solutions that might not be there, and it doesn't spend a lot of time finding a solution that is sort of fragile, and that if you tinker with your program a little bit, it'll pop over to a different space in the a different solution in the solution space. And that in turn improves predictability. And really, the thing is, the compiler could be doing a whole bunch of different things, but there's a design trade-off here. Make the compiler simpler, make the programming language more specific. Make the programming language more predictable, and in cases where type inference fails, it's really not that difficult to deal with. Just provide some extra type information, and it will let the program compile. And there we are. Okay?
Very good.
Okay. All right, on to the next one.
Right. Okay, so that one we thought that one was the hardest of the five. So this next one is like not the hardest of the five by any means. Why is set equality so weird Did you know set equality was weird? You're about to find out. Okay, so here's our setup. We've got we're going to make a hash set and we're going to put into it lowercase a and uppercase a. Then we're going to make a tree set, and we're going to use, for the comparator on the tree set, we're going to use a case-insensitive order, because we want to use this tree set for sorting strings in case-insensitive order. It's a very reasonable requirement. And then we're going to add all of the elements of, we're going to add lowercase a and lowercase b to the tree set. We've already got lowercase a and uppercase a in the hash set. And now we're going to ask, does hash equals tree, and does tree equal hash? Right? So what's the answer? What do you think the answer is? Should be, Stuart?
I don't think either are equal.
You don't
So
think
they should be false.
Well, they doesn't look like they're the same, right? So
No.
so they're both, yeah, right. That seems reasonable to me, but it's not what happens. You know, what happens is that one of them is false and the other one's true. Why is this? There's a pretty straightforward answer when you understand it. Each set implementation has its own rules for what constitutes a member of a set, right? And in particular, when two possible values would essentially be the same ones, because sets can't contain duplicates. What's the definition of a duplicate? Well, that is given by the membership contract, which can be called the membership contract, but in this section I'm going to call the equivalence relation. And the equivalence relation tells you when two values are equivalent. And a set uses its own equivalence relation to determine whether another set is equal to it. These two sets have got different equivalence relations, kind of obviously. For hash set, the values lowercase a and uppercase a are not equivalent, and for the tree set, because it's case insensitive, they are equivalent. So let's have a look at how the JDK in detail actually implements set equality. It does some kind of obvious things. It checks to see if it's asked whether set B is equal to set A. First of all, it looks to see, is set B a set? If it's not, then they're not going to be equal. And if they're not equal size, then clearly they're not going to be equal. But now, to find out whether they actually contain, quote, the same elements, it's going to iterate the elements of set B, and it's going to, for each one of the elements of set B, it's going to ask, does set A contain does set A contain that? And if they're all contained, then because they're the same size, right, they should be equal, right?
Mm-hmm. Yeah. So what does contains really mean here?
It's pretty straightforward. It returns true if set A has an element equivalent to this element of set B. That's how else could set A decide whether or not it contains an element? It looks to see, does it already have an element which is equivalent to set?
Okay, but what does equivalent mean now?
What does equivalent mean? I already told you what equivalent means.
Well, I wasn't listening.
Stuart. The equivalence relation that it uses is the equivalence relation for set A. Well, that's the only one it has, right? It's perfectly reasonable. So if you want to see why tree equals hash, so tree in this case is set A, and tree says, according to the case-insensitive order, it definitely contains lowercase a, because it does contain lowercase a. And it also, according to the case-insensitive order, it contains lowercase b. Sorry, uppercase a. No, uppercase. It contains uppercase a because they're equivalent. So tree equals hash.
Why haven't we fixed this?
He said we this time. Did you hear that?
I know.
Why haven't they fixed this? It's obviously wrong, isn't it? Equality clearly should be commutative, right? It's just it really doesn't make any sense. So, why? I mean, surely we could just get rid of this problem by insisting that set A should contain every member of set B as it does now, but also that set B should contain every member of set A. That's just obvious.
Well, I think it's worth a try.
Okay, let's give it a try. Okay, so now we're going to indulge in in big decimal, which is like always the one that we pull out when we want to make something really weird. So we're going to make a tree set of big decimal, and we're going to use for the comparator of that tree set, we're going to use a scale method on big decimal. And two big decimals are the scale method of big decimal returns the number of fractional digits in the big decimal. So two big decimals are equivalent if they have the same number of fractional digits. So we're going to add to this scaled tree set, we're going to add a big decimal of 1.0 and a big decimal of 1.00. The scaled method returns 1 for the first of those and 2 for the second. Okay? Now we're going to make a tree set of big decimal using the natural order. That's the last line that's on there. Two big decimals are equivalent according to natural if they have the same numeric value, right? So you've got an inkling of what's coming here. And we're going to add to this, we're going to add a big decimal of 2.0 and a big decimal of 1.0, right? And now, so we'll check that scaled looks right. Scaled does look right now. The scaled set contains 1.0 and 1.00. The natural contains the 1.0 and 2.0, just as we put them in. So, right? So now let's ask, does scaled equal natural, or does natural equal scaled? What do you think, Stuart?
Clearly, these have different elements, so neither should compare equal to the other. I mean, that's what you would think, right?
Well, yeah. I mean, that's why we wrote this whole thing about having to check both sides.
Yeah.
Right. I hear chuckles, and I'm not surprised because when I saw it, I thought, "Wow, that really is weird." But it actually follows perfectly logically. As far as scaled is concerned, what it does is it looks at all of the elements of natural, and it asks for each of the elements of natural, do I contain it? And the answer to that question is yes, because as far as scaled is concerned, elements are equivalent if they have the same number of fractional digits. And 1.0 and 2.0, both of them have the same number of fractional digits as 1.0, and so they're equivalent to it. So scaled, as far as it's concerned, does indeed equal natural. Same size, contains all the elements, passes. Okay? Why does natural equal scaled? Well, natural equals scaled because it's got in it, it has two elements of this, sorry, I'm reading it the other way around. The sets are in the same place. Natural looks at 1.0 and it says, well, I've got that there because it's the same size as my 1.0. And then it looks at the element 1.00 on the left and it says, oh, I've got that one as well because that's also the same size as 1.0. So, right, as far as natural is concerned, it also contains both of the elements of scaled.
Right, so at least equals because it's commutative now.
Oh, right, okay, that's good. That's definitely an advance. It's commutative, it's just wrong. It'd probably be fast as well. Maybe we just made this mistake of allowing these sets to have this weird equivalence relations, right? I mean, perhaps there's nothing wrong with the algorithm, but we just shouldn't have sets with these different equivalence relations. What is the point? Well, the point is that they're really useful. I mean, a lot of the time, it's actually what you want. I mean, supposing, for example, you do indeed want a set of strings, and you do indeed want to sort them in case-insensitive order. I mean, a navigable set of strings. I mean, the navigable set is just like, it's a great data structure. It's really good. It's useful for all kinds of things. And sorting is obviously a really useful thing to do with it. Often you do want to sort strings by case-insensitive order, but in that case you can't have lowercase a and uppercase a if they're equal in the sort order. you can't then choose a precedence between them, so they can't both be present. Case-sensitive order says they've got to be the same. So in other words, the set can't contain both of them. So it's just a perfectly reasonable requirement to have. So that's one of the kind of common non-equals equivalence relations that we have in sets in the JDK. Another one is in sets that are formed from an identity hash map. And that also is perfectly reasonable, because what that is used for typically is if you're constructing an object graph. If you want to list all of the elements of an object graph, you're following the pointers, the references, from one to another. And if you hit a cycle, then you want to be able to stop because you've already seen that element, right? By the time you come around the full cycle, you've seen that element and you want to stop. Well, there's no point in asking, is this element equal to one I've already seen? Because that could be some element somewhere else completely, and you would want to continue. So what you really want to ask is it the same element as one that I've seen before? Are they actually identical? And in that case, it's object identity you want and not equality. So here's another set that has the wrong equivalence relation, or a different one, as I would say.
Right, and some of you may be familiar with the specification wording that talks about consistent with equals, and I think these are both examples of sets or maps, as the case may be, where the equivalence relation is not consistent, or it is inconsistent with equals.
Inconsistent with equals, yeah.
And it's like the problem is, you have some weird semantics associated with it. On the other hand, they're very useful, and I think these are the use cases for them.
Right. So, I mean, the spec is actually, I think the spec is not great. Not great at this point. It just says weird things will happen, but it doesn't say what they are, and it doesn't actually say why. And it says, you're recommended not to have the natural order be inconsistent with equals, but the spec is not explicit about it. Whereas I think it actually could be a lot simpler. So a way of testing set equality that wouldn't rely on the equivalence relation of either set, because that's always going to be asymmetric. Maybe what we could do is try to establish that there's a one-to-one correspondence between pairs of equivalent elements, where not using the equivalence relation of either set, because that takes us back to where we were, but supplying an equivalence relation as a predicate. It would be a parameter to equals along with a custom hash code. All right, this is going to be obviously really a different idea of set equality. I guess it would kind of clear up the semantics.
Yeah, you could add a method on the collections class that says, are these sets equal according to this predicate? Yeah,
that would work. But the problem is, it would also be phenomenally slow. Now, it's order n factorial, and we're not going to try to explain why, because you want to get away at 4:30. So that's the issue with set equality. I mean, they haven't fixed it, because actually there's nothing to fix. The way that these behaviors that we saw there, which look so weird, basically what they show is that set equality, asking about set equality, simply doesn't make sense for sets with different equivalent relations. So, like, the things that I was putting up there were nonsensical, and you just have to get over it.
Get over it, Maurice.
I don't have any problem getting over it. I'm used to this now. As far as I'm concerned, the problem is that the spec is really not very clear about this. And actually, there is some. Why haven't they fixed that?
Yeah. There's a bug that's been open for a while on this. Yeah.
Okay. Is that a fact? I can also recommend a discussion in this book. Where, oh, by the way, I didn't say about this book. I should have said this is like, okay, I've written the second edition of it, but actually Stuart was a technical editor, and it's really a collaboration in a big way. Okay, so that's set equality.
Okay, all right. Now
we're number 5.
Yeah.
Blimey, we got that.
Well, Well, good. Okay. So
what happened there? We've really made up a lot. We made up a lot of time.
Faster. Yeah. Okay. So immutability. Okay. On to the next thing. So if immutability is so good, why doesn't Java support it? Okay. So well, let's examine the premise of this. Immutability is good. And the reason is that it makes it easier to reason about state. It allows structural sharing without doing lots of defensive copies. Immutable things are thread safe. And something that there's another thing lurking around in there is that if something is immutable, then the JVM can optimize it well. And you can do things like constant folding. And so that everybody likes their programs to go faster. So if you have things that are immutable, then you want the JVM to be able to optimize it. Okay, so let's say, since immutability is so good, let's take ourselves the task of making an immutable object in today's Java programming language. Okay, so what do we need to do? Well, first thing to do is to make all the fields final. Okay, and then that has some certain side effects, which means that all the fields need to be initialized by the constructor, and I think people are pretty used to that. Another one, though, that is not obvious is that you need to prohibit or restrict subclassing, because if you have an immutable class and you allow anybody to create a subclass of it, they can add a mutable field, or they can override methods that make the object appear to mutate. So you want to avoid that, so you need to either make the class itself final, or you need to make it a sealed class, or something like that. Okay. Now, if you have any mutable elements that are pointed to by your fields, then you need to do some extra work here. You need to make sure they're confined. Not only do you make sure they're confined, you need to make sure that you don't mutate them yourselves, and if you properly encapsulate them, then nobody else can. And so that's how you can make sure that mutable things cannot be mutated. And that's a lot of that's a lot of work that you need to do, and you have to if you want to make something immutable, you have to examine it very carefully. And if you make a mistake, then it's just a mistake. You don't get any errors or warnings.
Honestly, you could do better. I'm sure. Like we've got this really sophisticated language. It's been there for 30 years. Everybody knows immutability is a really good thing. Why don't you support it in the language?
Oh, sorry. There we go. Why haven't they fixed this?
Why haven't
we fixed it? Yeah.
Absolutely.
Okay. All right. Well, let's take a stab at defining an immutable class in the language. So let's just cook up this idea of adding a modifier to a class, and it has it has some effects, right? So it does the obvious things, like it says, okay, all the fields are final, and that of course implies that they need to be initialized by the constructor. And now it's like, okay, if you really want this to be immutable, then every type that a field has also needs to be immutable recursively. Because if you have something that's immutable, but it contains something that is mutable, then the whole thing isn't immutable anymore, right? Is there something about Schopenhauer's law of entropy, right?
Oh, right. Yeah. You and that.
Yeah.
Yeah. That's going to rule out collections, right?
Yes. Unfortunately, right? So there's some restrictions here, right? So not only does it rule out collections, but it also, there's a bunch of restrictions here. Any subclasses, what do you deal with subclasses? Okay, subclasses also have to be immutable and recursively immutable, and they can't have collections in them because we don't have any immutable collection types. Okay, so there's kind of a nested, why haven't they fixed this in here, which I think we answered last year. So include by reference our talk from last year, which is why aren't there, why don't we have unmodifiable, or why don't we have immutable interface types in the collections? But there's a subtle point here, which is that mostly when we talk about so-called immutable collection types, those are really just interfaces that don't declare mutator methods. That doesn't actually mean the same thing as immutable as we have here, which has all these language implications, right? So So we have to be very, very careful of our semantics. So in particular, so other collections frameworks like Guava, Eclipse collections, and Kotlin and so forth do have immutable collection types. But basically, they're immutable because it says so in the contract, or it says so in the specification of the class. But in fact, there's nothing like this language support that we've cooked up, which says an immutable class has all final fields, and all of those types are recursively immutable in the same sense. So those are really actually distinct things, and it's very confusing that they're identified by the same word.
Yeah. So, I mean, you could implement one of these immutable interfaces with a class that's got mutator methods on it. Absolutely no problem there at all.
Right.
I mean, contracts are important, but this is not but they don't mean much to the JVM.
Right. So they're definitely useful, and this is not a criticism of these other classes, but also it's not that it doesn't give us the same guarantee that we're fishing for in this strawman proposal for the language. Okay, and in fact, if you look carefully at the programming language, or after you look at the whole JDK, you start to question whether anything actually is immutable in Java, right? So we talked about collections before, but so certainly the JDK does not have any so-called immutable collection types. Okay, granted, it doesn't have those. Suppose it did. The implementation of the collections would probably use arrays, and arrays are inherently mutable in Java. So can you build something immutable? Like, okay, so remember, we have the strawman where an immutable class has all final fields and all its types are recursively immutable. Fundamentally, you can't put an array in there because an array is mutable. So an array cannot be immutable in this proposal. Okay, what are we going to do there? All right, so that's a problem. Okay, now there's string. So string actually stores its characters in an array. But there's another thing about string, which is that it has a mutable hash code field. So the hash code field is a cache of the string's hash code, and it is not final. It's like, what? Why isn't it final? Because it never changes, right? Well, blah, 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 benign data race, right? So the computation of the hash code, any thread will compute the same value. And it turns out that even if they're racing threads, they all come out with the same result, et cetera. And so we lazily initialize the hash code of string, and the first thread to compute the hash code writes it into that value. And even subsequent threads that compute it will write the same value. So that's OK. But in fact, we don't want to pre-compute the hash code of every string, because that would slow down string creation, and not every string has hash code calls on it. So we have lazy computation of the hash code, but that also means that the hash code field is mutable. And it's like, okay, so string can't even be immutable in our new language proposal. So that's kind of a problem. And then this isn't quite the same thing, but you may be aware that final fields can actually be mutated, right? So yeah, you can mutate them in a constructor, but once you've left the constructor, then they can't be mutated anymore. Well, yes, they can. Reflection can mutate final fields. Okay, so here I said string is observably immutable. So I'm introducing a new concept here. So our strawman language proposal was about what I'll call structural immutability. So you can make some very strong statements about structure. An immutable class is one that has all final fields and one whose fields are also typed immutable. That's a great statement about the structure. Okay, but it turns out that nothing in Java actually really is structurally immutable. It's all things that are immutable in a different sense that are built on top of mutable constructs.
So this idea that you've had is basically 1, impossible to implement, and 2, undesirable even if you could. Have I got that right?
I think it's actually possible to implement, but it wouldn't be useful. Because the object that we actually build aren't structurally immutable. They're more like observably immutable or logically immutable. But basically, like string is built from an array and from a mutable hash code field. So it has mutable pieces in it, even though we all know that string is immutable. What do we mean when we say string is immutable? It means that its value cannot be observed to change. So that's why we say it is observably immutable, even if it is not structurally immutable. Okay. And then structural, yeah, how do we get into the arrays here?
What we're asking is, what we're asking is, if we could make arrays. I mean, I still think that actually your structural immutability can't be achieved because we can't make arrays structurally immutable. You'll always bottom out on something that is mutable.
Right.
And then Schopenhauer's, we won't talk about that. So, but what we actually want from these arrays is actually, I mean, the desirable thing is observable immutability. Because if you can't see that it's immutable, then that's clearly what apart from telling the JVM about that, that's clearly what you want for everything else. So since arrays are the problem, I mean, they're the biggest problem. We can ask, what would an observably immutable array look like? And in fact, this has been. They have been thinking about this.
Yeah, so there's been a lot of thoughts and proposals about this. But one of the things is, if you want to create an immutable class, I mean, final fields definitely play into this. But the thing about an immutable class, or an immutable instance, is that you get the opportunity to initialize the final fields in the constructor. And arrays have no constructors. So yeah, it would be nice to have an observably immutable array, but where's the constructor where you can put the initialize into it? Okay, so now John Rose, one of the JVM architects, came up with this concept quite a while ago called a frozen array, which is basically you just take a regular array and initialize it however you want, and then from a fully initialized regular array, you can create a frozen array, which is an immutable snapshot of it. And that's nice. I think that has good semantics. It's very well defined. But the problem is, in order to initialize an array, you have to create a second array and copy it. And that's kind of why we haven't gone forward with that, because we tried to apply that concept at certain places in the JDK, and we said, well, it's just going to slow down JVM startup terribly because we're going to be making these array copies everywhere. So I think we need to work harder at figuring out our array story. Okay, observable immutability. I think the key point here is that it's a logical property of an object, not a structural or a physical property. So observably immutable things can be built from mutable parts, and things are encapsulated. And I think, okay, so we talked about this already. String and big integer are good examples of things that are observably immutable, but that are not structurally immutable. And so this is what we really want. As Java programmers, we really want things that are observably immutable, but we want to, for implementation reasons, we want to reserve the right to mutate things in a very, very controlled way encapsulated inside the object. And so that's why this idea of structural immutability is really easy to talk about and not too difficult to specify, but it's actually not that useful. Okay. But there is a problem with observable immutability implemented this way, which is that if you have things that are built out of mutable parts, then you don't get the optimizations that the JVM can supply, like constant folding. Because the JVM, as a programmer, in your mind, you say, I'm going to initialize this array once and never touch it afterwards. The JVM doesn't know that. The JVM can't read your mind. And there's no way you can tell the JVM, I'm not going to, well, not yet at least. You can't quite today you can't quite say, I'm never going to touch this array again. So that's kind of the loss there, which is we've lost the JVM optimizations with observably immutable things. Okay, so there's this variation that we've spoken about before in the past, which is since we really don't want structural immutability based into the language, and this idea of observable immutability is kind of a logical thing, it's pretty squishy, it's hard to define, what can we do in the language and libraries to provide at least some support for this? And the answer is unmodifiability or maybe shallow immutability. So instead of having something be recursively immutable, just say, okay, well, we can something that is recursively immutable, it's a global property of an object graph, right? So if you have an immutable object that refers only to other immutable objects, that's a global statement about an entire object graph. And global statements are hard in a programming language. But saying, okay, this class, the things in this class cannot be mutated, that's a local statement. And that's what we mean by unmodifiability. And that's actually, that's a less powerful characteristic than, say, structural immutability. But it's also tractable to define in the language, and also it's easier to reason about. So maybe it provides a step in the right direction. Okay, so in fact, there are a bunch of things in Java that are unmodifiable in this sense. So we have our unmodifiable collections, we have records, we will have value types in Valhalla. And so the point there is that even though you might say, oh, Valhalla objects, value objects are immutable. Well, you can still have one of those pointing with a reference that points to a mutable object, just like you can have that with records, or in an unmodifiable list can have a reference to mutable objects. But the first level is unmodifiable. And so there's a new thing that's called lazy constant now, and in the previous release it was called stable value, that provides some interesting characteristics, which I'll talk about later. And then there's also a proposal on the table to fix final, and to make final mean final. So this time we really mean it. And so this is not a solution for immutability in the sense that we've been talking about, but you can see we're working on some stuff around the edges, and there are some useful useful mechanisms in here. Okay, so let me briefly talk about records. Okay, so a record is unmodifiable. All of its fields are defined as final by default, but there are some rules about using them effectively if you do want your data to be unmodifiable, and that is you need to make defensive copies of things in the constructor. And so if somebody passes you a list, you need to do something like list.copyOf before storing it in the field. And so with some care, a record or a graph of objects under a record actually can be made observably immutable. So that's helpful. And really what you need to do is make defensive copies in the right places. Okay, so some discussion about value types here. All right, so there's a lot of there's a fair amount of subtlety here compressed onto one slide. So let me give it a go. So first of all, in a value type, it's a class. All fields are implicitly final, but there's this problem, which is that all fields are initialized by bytecode, and the bytecodes are out of control of the VM. So what it means is that there's a state, if you create a value type, there's a state where, in fact, it actually is mutable. Now, if you think about regular classes, how do you initialize final fields? Well, the bytecode verifier ensures, okay, so the rule is that a final field can only be assigned within a constructor. And the bytecode verifier ensures that. If you write to a final field, if it's in a constructor, it's allowed. But if it's outside of a constructor, that's disallowed. But there's this problem, which is that it's possible with regular Java objects for an object to escape construction while it is still being constructed. And so suppose I have a constructor that's initializing some of the final fields, and then it calls some method and passes this somewhere. Well, so now somebody else has this, and if they start reading fields, they can observe final fields to change. And that's a big problem. And so JEP 513 is this new thing. It's called flexible constructor bodies, which basically says you can do things before calling super. But what it enables is a weird, well, it's not weird. It's actually a new phase in object construction where fields can only be written but not read, and this, the reference to this object that is currently being constructed, cannot escape. And so between that and this JEP draft here about strict initialization will enable Valhalla value types to be initialized by bytecodes, but it will also ensure that that no other thread will ever see an object when it's in this intermediate state, which we call, well, I'll get to, yeah, so I do have I call it a larval form here. This is what we call it, like if you're talking about a butterfly, right? It hatches an egg and you get a larva out of it, and then it metamorphoses into the adult thing. So that's the idea of this object. When an immutable object is in the midst of being initialized, it's like a larva.
It's a caterpillar.
It's a caterpillar. That's right. Yeah, and then when it leaves the constructor, then it becomes kind of a mature object, and every field is fine. And the key is to make sure that nothing outside of the constructor can ever observe the value object when it is in its larval state. Okay, so these things. So this is one of the reasons why Valhalla is taking a long time, because there are a lot of thorny issues to work through here, and the reason we want to do this is we really want the JVM to say, I'm dealing with a value type. I want to be able to store this field in a register. I want to store this field in a stack, and it's not going to exist on the heap anymore. And it can only do that if it can be absolutely assured that no thread anywhere else has seen this value object in its larval state. Because if it needs to support that, then that means it has to be somewhere on the heap, and other threads can do it. So we really want to enable the JVM to do these optimizations, but in order to do that, we need to change the language and the JVM construct to support it. Okay, I hope that made some sense.
Some sense.
Yeah. Okay. So make final mean final. So there is this problem historically that final fields are actually mutable. By default they aren't, but you can mutate fields using reflection, and you can call set_accessible on a field, and not only does that defeat access control, so you can get access to private fields, but if that field is final, then set_accessible will say, oh, well, I'm going to let you write to it as well. And so historically, this has been a big problem, because people look at JIT compilers and they say, well, gee, this is a final field. Why isn't the JIT optimizing this? Why does it reload this field anyway? It's never going to mutate. It's like, well, because reflection might change it. Oh, nobody does that. It's like, yes, they do. Okay, so why do you think?
What is the API that requires objects to be created without being properly constructed?
Are we going to give a free book to the first right guess? There he is! Yes! Somebody in the middle said serialization.
It's all, the answer to every question about why things are so difficult is always serialization.
Yes. Okay, yeah. So so this is a problem. Serialization actually, well, there's Java serialization and then third-party serialization frameworks built up a history of needing to mutate final fields. And so here we are. So the way we are getting out of this is, there's JEP 500. You can go read all the details about this. But basically, at a certain point, we're going to say, set_accessible is no longer going to disable finality. And of course, if your object is serializable, then somebody might want to deserialize it, so that won't apply to serializable classes. But for non-serializable classes, final really will mean final. And then the JVM can say, oh, this is not a serializable class. I'm going to do these constant folding operations. So the hope for this is that, final is restored to its former glory, and the JVM can do some good optimizations for us there.
The former glory that it never had, by the way.
Well, I think this was actually added sometime in 1.4. So, although that's true, the JIT compilers probably didn't do as much optimization back then as they do now. Okay, so there's this new thing I mentioned previously called lazy constants, formerly called stable values. There's a JEP for this, and you can definitely go read about that. But here's an interesting thing here, because we like lazy initialization, because if you require something to be initialized eagerly, then that's a definite amount of work you need to do. And there's this principle, which is if you don't need if you don't necessarily need something now, postpone it, and that makes startup time faster. And in fact, there's a possibility that you'll never need it, so we can save work overall. So laziness is good. Okay, but then the problem is, if you want to lazy initialize something, then it kind of needs to be, I mean, the easiest way to do it is just to put it in a mutable field. Oh, if it's null, then initialize it and store something in there. And that's done after construction time, so it can't be final. Well, and then that defeats constant folding optimizations. And then there are various ways, like the class holder idiom, to say, oh, okay, well, I want to do this as class initialization time, and I create a nested class, and then it's just, right? So you can do it, but you have to write a whole bunch of code in order to get a field actually to be lazy initialized. So the lazy constant JEP, which is forthcoming, it's another preview of stable, it's just a rename of stable values, but the concepts are all the same. Basically, it allows lazy initialization, but it's also a special construct that says after a lazy constant has been initialized, it can actually be treated, so it's lazy initialized, but it's also treated as a constant by the JVM. So we get all those nice constant folding optimizations. And so that's the benefit there. And then lazy constants also has fixed size lists and maps. And so you can have like a map that has, you can design a fixed set of keys, and the values will be lazy initialized, but then they will persist and be constant folded by the JVM after that. So that's really powerful. Okay. So what's the summary here? So we don't have structural immutability, and it's not actually as useful as you might think. What we really want is observable immutability. And there are a bunch of constructs floating around in Java that nibble around the edges. So we're making it easier and more flexible to have, we're providing mechanisms that are easier and more flexible to let people write things that have observably immutable properties, but there are all these special cases and stuff. So you see this wide variety of constructs that we are adding to the JVM and the language and the and the libraries. And so maybe we are still thinking about frozen arrays or some kind of observably immutable arrays, and that's still on the table, but it's actually more difficult than you might think it is. All right, so that's the end of the.
So the summary is that this is one which they haven't fixed, but actually they are thinking about fixing it.
Yeah. Well,
it's a bit better than some we've seen.
Yeah. Yeah. So it's not necessarily fixed. So I don't think we'll necessarily get a keyword that says I'm going to make this object immutable. But I think with the variety of mechanisms that we're providing, I think that actually gives us some more flexibility in implementing observably immutable objects. Okay.
Right. Wow.
All right. So here, you want to do those? Yeah.
Astonishingly,
yeah.
we've got to the conclusion of this talk with time in hand. Yeah. We were so panicked at the half time that we were going to run over that we've raced through it with lots of time for questions. So. The conclusion is, why haven't it fixed these problems? Well, the answer is, I think you probably should have got a fairly clear impression. These are hard problems for the most part, and in some cases, really, really not fixable. So hopefully, although we haven't solved them, in some cases we've seen some progress towards solving them, and even thinking about them has actually, I hope, kind of shown you why they're hard and what's interesting about the way they're hard. We've found workarounds and coping mechanisms for all of them, really, in effect, sometimes more effective than others. And we've noticed that there actually are, even though they haven't fixed them, they actually are very conscious about them and are actually doing something about it. So it's good. And we hope we have a deeper understanding of the issues. So
I think that's we're all here. Yeah.
Yeah, and that's the answer to the question: why haven't they fixed this? Okay, so that's us. We're on to Q&A.
Okay. Okay, great. Thank you. Yeah. All right. So I saw a hand right there. So I shout out the question, and I'll try to repeat it for the recording.
described mostly because there are different ways to ensure the to make the comparable thingy.
Yes,
Ways to compare whether the values in the sets are unique, right? Why not compare when comparing the sets on whether or not they compare those values at the same way, in the same way?
Okay, so the question is about set equality, and so let me try to restate it, but I'm also not sure, right? So the question about set equality, and so at the outset we said there are, in the segment of the presentation, each set has what we call its equivalence relation, which defines, we always say sets can't have duplicates. So how can you tell whether two sets are duplicates? And different sets have different relations that determine whether two things are duplicates. Okay, so with that set up, is there a way you can clarify your question? I'm still not quite sure what you're asking.
Yes. Why not, when comparing those sets, check whether they have the same way of determining duplicates?
Okay. Yes. So the question is, so now we're saying we have set A equals set B, and so can you ask the sets whether they use the same or different equivalence relation? Actually, that's a very good question, and it has a fairly deep answer. So it can be arbitrarily difficult to determine whether two different equivalence relations are in fact congruent. So for instance, suppose we say, okay, so there are places in the JDK, like in tree set, where we say we actually use we get the there's certain cases. I think suppose you have a tree set, and then you say add all on another tree set. There's actually some code in there. I think it's this case. There's some code in there that says, oh, if I'm empty and if the other guy has the same equivalence relation, doesn't say this in the code, but this is essentially the gist of what you're asking. If it has the same equivalence relation, then I'm going to use a fast path. Otherwise, I'm just going to iterate the other set and add them one at a time, because I don't know what order they're going to come in. His order might be different from my order, so I have to add them one at a time. Okay, so it uses identity. So it uses the identity comparison on the comparator, and that works for things like string. Okay, so in the string class, there's string.case insensitive order, and so if you have a bunch of collections floating around that all use the actual identical comparator, that will actually work. But if you say comparator.comparing something, and then again over here you say comparator something, you actually get different instances of things that compute the same thing. And so this fails. And all you have is references to a function. Now, I don't know for a fact, but I believe that if you have two functions, even if you were to crack open the bytecodes or whatever and look at them, it is undecidable to determine whether two computations are in fact equivalent.
Yeah.
So that's the deep answer, which is it's undecidable. But there are a couple shortcuts, which is since we represent functions as objects in Java, two objects that are equal are in fact completely equivalent. So, but there are cases where you can circumvent that. It's also a little bit hard to tell whether two different collections use equals. So for instance, hashmap uses equals, object.equals, and that's fine. But there are also a lot of things. So this gets back to the stuff in the spec about consistent with equals. So you can so we showed examples of tree sets like that use the case insensitive comparison, where the comparison was inconsistent with equals. And so that means if you call compare and it returns 0, it returns 0 under different circumstances where equals returns true. But there are actually a lot of comparison methods that are consistent with equals. Like a straight lexicographical comparison on strings is consistent with equals. So if you call compare on two different strings case sensitive, and it says 0, then equals is true. And vice versa. If two strings are equal, then this comparison method is 0. How do you look at a comparison function and say, is this consistent with equals? I think that's also undecidable.
Sure, it is.
Okay.
Yeah.
So yeah. I think he gets a book. Come by afterwards. So good question. I hope my answer was satisfactory. Okay. Yeah.
We have a question.
Why haven't they fixed string formatting? You know, the string templating Jeff was the first one that was removed from Java 23, I think. But is there something new coming?
String formatting and string templating. I'm not terribly close to that. So from what I understand, there were two big concerns, two big goals that the string templating effort was trying to provide. One was that it was trying to provide high performance, but another was that it was trying to provide safety. In particular, one of the things about string formatting and string templating is that it's really easy to open up security holes if you use such a feature indiscriminately. And I think a good example of that is the log4shell vulnerability, where basically it said, oh great, we have a nice logging framework, and then we have a way of inserting values into log messages, and then somebody had the bright idea, oh, let's evaluate expressions that can be inserted into the log output. And then there's a short step from there to remote code execution vulnerabilities. Okay, so I think that's the kind of thing that we want to be on guard for. And there's some hand waving about, well, if you do it this way, then somebody's going to have to write some code. But then you need the possibility of you need any string formatting code that you plug in to be able to verify its arguments sufficiently or provide quoting or something like that in order to provide that safety. And so that's kind of the idea. But I think just the crashing of those two requirements made the resulting. There are some things that were uncomfortable about the resulting design. And if you look at the evolution of string templates over successive previews, it shifted around in some weird ways, and it kind of got complicated, and some things got simpler, right? And it was sort of bouncing around in some design space. And I think what we said was, it's like, this doesn't feel like it's converging. And it's like, yeah, this kind of fulfills the stated requirements, but if we made this a final feature in the JDK, I think everybody would actually be unhappy with it. And so we took it out. Now, is there something coming? I think there's some ideas for alternatives that people are cooking around, but we don't have a preview JEP on deck. And I think the answer to that is the people who are now working on string templating, or who would be, or have some ideas about working on string templating, are actually all busy doing other stuff right now. So unfortunately, it's not like something is going to pop back in the next 6 months.
Yeah, Andy.
Isn't there a case for classes like string, which have hash code, cache, and big integer and big decimal, which cache their string for the two-string method? Isn't there a case for expanding private defining to include entirely private variables, entirely private references to be assigned after construction? If not, why not?
Okay. So yeah. So the question is, if you have something that's a private cache of something, and so it preserves observable immutability, shouldn't you expand final to encompass that? Well, not exactly, but you're right. That is exactly a use case, and that is the use case for lazy constants.
Well, no, it's not.
It's not.
No, because lazy constants are by the definition static.
They're not.
Are
they?
I don't think so. No, I think that's the idea. That's the idea of lazy. And if I don't think I don't think they're static by definition. I think the common use case is to make them static to enable certain constant folding optimizations. But if you do have a field if you have an instance field that is lazy initialized, you should be able to use a lazy constant for that and get the benefits of lazy initialization. And maybe the JVM won't be able to optimize it today, but it might be able to tomorrow.
But isn't that a bit of a hick hack? I mean, you've got a stable value or a lazy constant, and you're actually need to be able to evaluate that when you call a two-string method in big integer or big decimal, or the hash code method of string, which kind of like defeats the object.
Okay, so I think we're kind of digging into this a little bit. I don't think it defeats the purpose of it because you can write the same code that does the lazy initialization, and even if it's an instance field, I think there's the potential for the JIT to do the optimization of once it's been initialized, then it can cut out the extra method call and Boolean check and stuff like that, even if it can't actually fold the result in as a constant. So I think there is some benefit for using lazy constant as an instance field. And if there isn't today, and maybe somebody can crack open the code generated by the JIT compiler, and I think people should do that because they want to have things go fast. There's I think that lazy constants have the semantics that enable that to happen, even if today's JIT compiler doesn't do it. There may be a possible enhancement, and the compiler folks are always open to these kind of things. It's like, oh, you need to do constant folding in this case. And it's like, oh, well, we can't do constant folding because blah, 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 blah. So maybe we need to change lazy constants in such a way that it does enable that optimization, which is why it's in preview now. And so we still have the opportunity to change it. Or maybe change the implementation to enable it in the future. So.
Yeah.
Sorry, just to add to this. Probably the specificity was the fact that scope value, sorry, it was confused with scope value, I think, because scope value that is static.
Okay, so yeah, so there.
I it might be confusing. I mean, because I never heard that the lazy constant is static.
Yeah, pass over.
Yeah, so we have a clarification, and I don't know what was in the original questioner's mind, but in fact, I do get scope value and stable value mixed up, and so I think that's one of the benefits of renaming lazy constant, because we don't have two things that are named SV that have kind of sort of similar sort of uses and constructs, and I think the idea is that there's a different thing called scope value, which is now final in 25, if I'm not mistaken. And those typically are static because those are kind of the moral equivalent of thread locals, and so you kind of want those static so that everybody uses the same one.
Okay. Yes.
Imagine that you reach the point when JVM can detect observably mutable classes to the optimizations. In this case, do you foresee language mechanism to also test that certain class is observably mutable, like a construction?
So there's a question about the JVM detecting observably immutable classes, and then do we have something in the language for providing observable immutability?
So you'd have to detect observable immutability by looking at the properties, the kind of the behavior of a class, the things that the class could do. So we'd have to reflect on the class to kind of figure out whether or not it could be whether it could be mutated. I think that's going to be really hard to establish computationally. I mean, you think about string and the hash code. I mean, that's kind of...
Yeah.
I mean, it's hard to imagine any automatic reasoning that could figure out that lazy hash code is in fact a benign data race.
Well, if you analyse the bytecode for methods that actually write to that, and it's written only once, almost functionally equivalent to a private final.
Yeah, right. So okay. So the follow-up comment is about can you analyze the byte codes to determine whether something is written only once? And maybe in the simplest cases you can, but I think you quickly run into the situation where you potentially get an undecidable computation. Because here you're trying to predict the outcome of something. But I think to the original question, I think that as I understand the thinking around this and the parts of the conversation that I've participated in, I don't think we want to have. I don't think we can. I think it's too much. It's too much to ask the JIT to detect things that are observably immutable. We want the programmer to declare that somehow. And the question is how the programmer should declare it, what constructs should programmers use to do that, and what semantics does that declaration have? And so one of the reactions to the lazy constant proposal is, oh, they just should have added a lazy keyword to the language. And maybe we will eventually, but I think the problem is when you add a keyword to the language, what are its semantics? And if you look at the difficulty in defining the semantics of stable value and then now lazy constants, I think the decision behind that is to say, instead of just trying to add something to the language, let's see if we can create a library-based construct that has useful semantics. And there's been a significant design cycles and changes in the design on the library side. And it's much easier to define semantics of things in the libraries than it is in the language. We don't know if lazy constants has the right semantics. I think over a succession of previews, we think it will probably end up with useful semantics. Maybe it's useful now, but I think that's why we preview, which is to have people tell us, I tried to use lazy constants in this way and I expected it to work this way and it didn't. That's incredibly useful feedback. So if anybody tries it out and it's not satisfactory, we need to know about that because we want to be able to fix it before it goes final. And so the idea, so I think the design approach is we probably want to have programmers declare properties of things that we want to be observably immutable. And we're starting off by creating library constructs that do that. Eventually they may end up in the language, but even the library is a test bed for things that haven't yet made it to the language. And I think it's too far of a stretch to say, oh, let's just define a lazy keyword in the language and then dig in, make a bunch of decisions. We're not sure at this point if we made a bunch of decisions about what a lazy keyword in the language would provide us, whether those would be the right things that are useful for programs. And so anyway, so that's the design direction that we're going in.
Speak up, please.
Could you expand a little bit on concurrent modification exception? Earlier you said that there are maybe some plans to provide this information about concurrent modification being made out of band, such as emitting some kind of observable behavior, observable event that GDFR can later locate or something like that.
Right. So the question is about the plans that will enable concurrent modification instead of there being concurrent modification exception, the iterators instead would warn an out of band warning and maybe continue.
Okay. So there's not much of a plan here. Okay, yeah. So yeah, you covered the question, right?
Yeah.
Okay. Yeah. So there's not much of a plan here. This is basically a random idea I've had, and so I understand that people have problems with concurrent modification exception, and right. So is there anything that can be done about it? Well, we have these different concurrent modification policies. Maybe you should use a different collection or whatever, but I think that there are reasons for concurrent modification, which I hope we've, concurrent modification exception, which I hope we've explained. But sometimes it's not the right thing. Maybe you have real systems have bugs, and sometimes bugs escape into production, and sometimes one of those bugs might result in a concurrent modification exception, and so maybe you don't want a concurrent modification exception to occur in production. Maybe you would rather have the iteration terminate early. I don't know. I'm kind of guessing here, but catching. Maybe actually I should do a search. Maybe people have written code that tries to catch concurrent modification exception and do something reasonable with it. But maybe, yes, it's nice to be. I think our philosophy is that inevitably programmers make errors. It would be good to tell programmers about errors as early as possible, like at compile time. But we can't in general. So concurrent modification exception is detection of a programming error at runtime. The question is what to do when the system has detected that error has occurred. And throwing an exception is not necessarily the right thing. And so I'm kind of asking the audience and the community to say, would something like this be useful? Right? So in cases right now where basically there's this the implementation of concurrent modification exception is very simple. Basically, the iterator keeps a counter and the collection keeps a counter, and when the counter is incremented when modifications are made. And if there's a mismatch, the iterator says, "Oh, somebody else has modified that. I'm in trouble. Throw concurrent modification exception." That's basically it. It's very simple. But we don't have to throw concurrent modification exception. We could do something else. Would it be useful to do something else? I don't know. What should happen to the iterator at that point? I don't know. Actually, there's this problem because usually it's thrown in the middle of a next call. You have to return something, so that's why an exception was thrown, but maybe there are ways to rejigger that. Anyway.
I'm just kind of imagining what would the API look like where if you had to actually inform the iterator, like this is what I want to have happen and this is what I want you to do at the point when you've discovered this thing. And I could imagine that that API might be pretty complicated. I mean, like if you're going to post to the JFR, how are you going to tell it that? If you want the iterator to just kind of give up and go away, how would you tell it that? This looks like a pretty big design space.
Okay. Well, I think I haven't thought about this very much, but I think the idea is that the design would be pretty simple, in that you would try to detect concurrent modifications in the hasNext call, and if you did detect it, if hasNext, there are a lot of iterator implementations where you do hasNext, and if you know you do have a next element, you cache the next element, and the next call simply returns it. But then what hasNext can also do is hasNext can also do the modification count checking, and if it detects this problem, it could throw concurrent modification exception. Or maybe if you set a system property, then it would say, okay, log a JFR event, and then, well, since we're in hasNext now, we just return false. So, it's not much of an idea, but maybe it'll be useful to somebody. And if it is, let me know. If I don't hear anything, I'll work on something else.
Yes.
Two questions. One, following up on this, you could add a new method which returns an optional, of course. If available, give next, for example.
What, for the iterator concurrent? Yeah, okay. Okay, so that question is, add a new method to the iterator to return an optional in the case that where currently we would have a concurrent modification exception, so that you next would not be in the situation of having to return something when it didn't have anything to return. Is that right?
Yes.
Okay, so that's the first question.
First question, and the second question is a bit harder, I think. You've talked a lot about optimizations, that they are very hard, for example with immutability. But why not try, I don't know enough about compilers and stuff like that, but why not over-optimize and then promote things to be mutable when a mutation method has been called.
Okay, I think, okay, so it's like, yeah, so it's a question, I'm not sure how to repeat it, but there's a question about optimization and over-optimizing final or yeah, to optimistically optimize, and yes, okay, I think actually do have an answer for that. So, okay, so the first one, you can imagine a different iterator protocol that returns an optional instead of next and has next. I think iterator is too entrenched. I don't think it's profitable at this point to change its API. But I think there's a possibility of one of the problems with iterators is that an iterator itself is mutable, and I've mentioned John Rose before, JVM architect, and he's thinking about Valhalla stuff a lot. And one of the problems is that an iterator cannot be a value object, and we do want to use value objects. And so another thing is, it might be nice to have an iteration protocol that is based around value objects. And the thing there is to say, okay, well, instead of having an iterator, let's have a cursor which has a different set of properties. Maybe it'll be an optional, but basically it'll encapsulate a value and say, oh, okay, and it'll have an additional piece of state that says whether a value is present or not. So it's not quite the same as an optional, but you can say, here I have a cursor, I want to advance it, and I get another cursor that points to the next location. So I think I don't know where that fits in the evolution of the JDK, but I think that kind of idea is floating around somewhere. But I think that we kind of have to support iterators as they are today forever, because they've just been in there for so long. But I think there's always possibility for something new. Okay, the second thing is about, is this in relation to make final be final and the difficulty of constant folding finals? Yeah, okay. Right, okay. So yes, so there is a point in the design space. The issue is we would like to constant fold finals, but because of the possibility of mutating finals, the JIT does not optimize them. And I should say here, when I talk about the JIT, I've been talking about hotspot. There are multiple JIT implementations. And so the designers of hotspot decided, you know, it breaks too many things. Actually, there's actually an option. I don't know, it's one of those minus XX blah, blah, blah things. And I think you can even do minus, I think you might have to do minus unlock diagnostic options to enable this. But basically, you can say, yeah, you want a constant fold finals? Sure. Go wild. Hold my beer. And so you can actually enable that in hotspot and see how many things break. But basically, I think the hotspot team did an investigation about that. And they said too many things broke, and so that's off by default. And I think nobody's investigated it. Well, sorry, nobody in the hotspot team investigated. Now, our friends and colleagues at Azul have a different JVM, and they do different things, and they have a different JIT compiler. And so they did give a talk about this several years ago at the JVM Language Summit. I don't remember the presenter, and I don't remember what year it is, but there's a talk from somebody at Azul who sketched an alternative design for solving this problem. And it takes takes a page out of the typical JVM compiler playbook, which is to optimize optimistically and de-optimize if something is detected that, that violates the initial assumptions of the optimization. And so, so the Azul folks actually did investigate that. And so basically what they do is they say, okay, we are going to take final fields and we are going to constant fold them. But when we constant fold a final field, we're going to leave a marker there so that if somebody changes that with reflection later on, we can de-optimize. And that's, you know, I applaud them for pursuing this design. I think it's a really interesting point in the design space. I don't know how well that has worked, and I'm not a JVM expert. I know that the hotspot team at Oracle looked at that, and it was presented in a paper. I encourage people to look at it. It's good work, but also I think it might not be worthwhile, because what that means is that, at least, okay, so I'm not a JVM expert, but the possibility is if you constant fold a final field, you have to do bookkeeping in order to de-optimize every optimization. And so even if nobody in your entire system ever mutates a final variable using reflection, the JVM still has to do a lot of bookkeeping just in case. And in fact, it has to do that because the next class you load might do some reflection and modify something. So the expense of actually keeping track of that is pretty high. And so different teams have different evaluations. I don't want to say the Azul guys are wrong. They have their evaluation. They did that. They presented it. I think it's great work. The hotspot team decided, no, we're not going to do that. So it's a good idea. Deserves investigation. But from where I stand, I can't tell whether it is or is not worth it.
Okay.
I think that's it.
We're out of time.
All right.
Thank you very much for your attention. As somebody we know says.
Thanks for your attention to this matter.
That's what Donald Trump said. But we're not saying that.
No.
We're just saying thank you. Hope you've enjoyed this talk.
Okay.
And have a great rest of the week.
Okay. Thank you. All right. Bye.